This is Larry Moore. I'd like to welcome you back to our biological wastewater treatment training series. Today we'll be looking at some more activated sludge process modifications. We introduced you to that in the fifth presentation, and we'll look at some more of those process modifications today. First one we'll talk about today is pure oxygen activated sludge. You don't see many of these because they're really quite expensive and really are seldom used. And most of the time when they are used, they're used by very large cities because they're very expensive, and generally the only way you can justify the capital and operating costs is if you have limited space to put the treatment plant. Then this gives you a great option to deal with the lack of space. But basically what we have is a plug flow reactor, and it's divided in 3 to 6 compartments. And on the left-hand side, you can see the gas is introduced into the first compartment, the influent and the return sludge are all introduced in the first compartment, and then they flow sequentially through the 3 or 4 or 5 or 6 compartments, and then the mixed liquor heads to the secondary clarifier for settling to take place. But it has a number of advantages that we'll talk about, but again, you pay for those advantages. Some of the design information, typically these are considered high rate activated sludge. We operate the reactor at a very high organic loading rate, about 100 to 200 pounds of BOD per day per 1,000 cubic feet of reactor volume, and 25 to 50% return sludge flow rate or ratio, and then mixed liquor solids usually somewhere around 3,000 milligrams per liter. Have short hydraulic detention time in the reactor, and I typically would suggest a sludge age in the range of about 3 to 6, 3 to 7 days. So we have small reactors and wastewater's on the reactor for a short period, but we can get excellent removal because we're operating at DO concentrations of around 6 to 10 milligrams per liter typically, and that helps us to be able to be effective even at low detention times and at high organic loading rates. So again, feeding pure oxygen gas into the headspace, and then we'll use mixers, mechanical mixers, that will entrain the oxygen into the mixed liquor, and we can operate at higher mixed liquor suspended solids levels, again, short detention times, and we can put a lot of treatment in a small amount of footprint. So again, because of the high DO concentration, the sludge is actually over oxidized, and we can do a lot more treatment operating at a lower sludge age and a shorter detention time. It's a complex operation because typically, again, large cities use these, and they'll generally, it's more cost effective to generate the oxygen on site rather than truck it in. But if you have to nitrify, pure oxygen is not the process for you. It's difficult to nitrify efficiently in a pure oxygen system because of the short hydraulic detention time, the short sludge age, and also because of the relatively low pH. Typically pH is about 6 to 6.5 in the reactor because the tanks are covered and you have a buildup of carbon dioxide in the headspace, and that carbon dioxide tends to depress the pH in the mixed liquor. And again, disadvantages are high costs. This shows you a mixer for pure oxygen reactor. The mixer again keeps the biomass in suspension and also entrains the oxygen into the liquid. Drawbacks, again, high operating costs, high capital costs. It's a complex operation. You have to have operators that really know what they're doing and are familiar with the process. The oxygen generation facility is complex. It's susceptible to operating and maintenance problems. And I'm familiar with one plant in Tennessee that's pure oxygen, and Just recently, they had the oxygen plant go down for about 4 weeks, and they had to truck in oxygen all during that time, and it became a real issue to keep the plant performing well. And there are also safety concerns when you deal with pure oxygen. So you can truck in the liquid. That would typically be, I think, more cost effective if it's a smaller pure oxygen plant. As I said before, we generally don't design plants like this for small facilities because of the complexity of the process. Or we can generate it on site using pressure swing adsorption, vacuum pressure swing adsorption, or cryogenic system. And typically that's what these larger cities will do. They'll generate it on site. But if you truck it in, the liquid oxygen will be stored in storage tanks, pass through a heat exchanger, and put the liquid oxygen into the gas phase, and the gas will be directed into the first compartment of the UNOX reactor. This is a brief diagram of the pressure swing adsorption process to generate pure oxygen, and just one of the ways that we can do that. All right, now let's talk about low rate activated sludge. As I mentioned, pure oxygen activated sludge is high rate activated sludge. You're operating in a very high organic loading rate, 100 to 200 pounds of BOD per day per 1,000 cubic feet of reactor volume. In conventional activated sludge or moderate rate activated sludge normally would operate at about 20 to 40 or 20 to 60 pounds of BOD per day per 1,000 cubic feet. And in low rate activated sludge, we typically operate in the range of 5 to 15 pounds of BOD per day per 1,000 cubic feet. So it's called low rate activated sludge because it's loaded organically at a very low rate. We operate at a very low food to microorganism ratio, and we also operate at a very long sludge age. Typically, we'll design the biological reactor to have a hydraulic detention time of about 24 hours. It can be a little bit less, a little bit more. And one of the advantages of low rate activated sludge is we can produce excellent effluent quality. So if you have stringent effluent limits and you're not a large city, then low rate activated sludge is a process you definitely want to consider. The SRT, again, normally 20 to 40 days, and because of that long SRT, long sludge age, the nitrifying bacteria are able to establish themselves quite well. Now, need to keep that in perspective, because even if we have a substantial population of nitrifying bacteria in our biomass, they will generally only be about 2 to 4% of the overall bacteria in the process. The heterotrophic bacteria are BOD removing bugs, carbonaceous BOD removing bugs that use organic matter as a carbon source. They dominate the biomass. They're even in a system that nitrifies well, they will be 96 to 98% of the biomass. But even with only 2 to 4% nitrifier population in the biomass, we can do an excellent job of converting the ammonia nitrogen to nitrate nitrogen. Again, low organic loading rate, and the volatile fraction of the mixed liquor solids is low because with the long sludge age, the biomass is overly oxidized. We're operating, and going back to the biological growth curve, we're operating in the endogenous growth range. And so very low organic loading food, the bugs are starving, they're dying, and they're using their own cellular material and oxidizing it to stay alive because they're in the starvation mode. Extended aeration activated sludge actually applies to several types of activated sludge system. We can call it extended air, and we can use a rectangular reactor. We can use mechanical surface aerators, or we can provide air by using diffused aeration. And we call that basically extended air. We can also use the oxidation ditch process, and we'll talk about it in a moment. That's a type of extended aeration activated sludge. Sequencing batch reactors are operated in the extended aeration mode. So when we say extended aeration activated sludge or low rate activated sludge, we're actually talking about a number of different treatment options available to you as a design engineer. Again, long SRT, long aeration time, which is going to increase the cost. So one of the drawbacks of low rate activated sludge or extended aeration activated sludge is high capital costs and have relatively high operating costs because we have a high oxygen requirement. As I mentioned previously, in activated sludge, the incoming BOD load is channeled in two directions. It's channeled into synthesis reaction, growing biomass, and it's channeled into the energy reaction to be converted to CO2 and water and other end products to generate energy for the bacteria. Well, with low rate activated sludge, most of the BOD will be channeled into the energy reaction. We're going to produce much less waste sludge, but we're going to have high oxygen requirements. Again, it operates at a low organic loading, 10 to 25 pounds of BOD per day per 1,000 cubic feet is mentioned here, but it's actually a little bit, I usually use 5 to 15 as the normal design range, and a real low F/M ratio, about 0.05 to 0.15. So as I mentioned, we'll operate in the endogenous range. As far as controlling the horsepower requirements of our aeration equipment, we look at mixing and we look at oxygen requirements. And in low rate activated sludge, mixing requirements usually will control the amount of horsepower that we need for aeration rather than the oxygen needs. Some state agencies require you to have at least 100 horsepower per million gallons of mixing intensity in the reactor to provide adequate mixing of the biomass. We can produce, again, excellent effluent quality. BOD and suspended solids definitely less than 20 milligrams per liter, and oftentimes each of those will be less than 10 milligrams per liter. Ammonia, nitrogen usually will be 0.1 to 0.5 milligrams per liter, and even in the winter it'll be fairly low when the nitrifier is a little more sluggish because of cold weather. So it does an excellent job of nitrification, so we get CBOD removal and nitrogenous BOD removal in extended aeration activated sludge. Oxidation ditch is, again, another type of low rate activated sludge. We have a racetrack channel. The biomass is moved around the racetrack channel by the rotating, in this case, rotating horizontal aerators. They impart a horizontal velocity to the water that keeps the biomass in suspension, and we'll try to maintain a horizontal velocity of about 1 foot per second in order to keep the biomass in suspension. And it typically, because of the high rate of water movement through the channel, it typically only takes about 5 to 15 minutes for the mixed liquor to make one loop around the ditch. So in essence, it operates as a completely mixed activated sludge process because of that short circulation time around the reactor. This is a picture of an actual, or two actual oxidation ditches. They're mirror images with each other. The one on the right, the flow is moving counterclockwise, and the one on the left, the flow is actually moving clockwise. So again, a racetrack or oval-shaped channel, maintain an average horizontal velocity of about 1 foot per second to keep the biomass in suspension. The influent is diluted quite a bit because the actual flow rate through the ditch channel itself will typically be about 20 to 40 times higher than the raw wastewater flow rate. So in other words, we got a 1 MGD oxidation ditch. The movement of liquid through the channel is probably 20 to 40 million gallons a day. That's just a physical movement of water through the channel. And it takes that kind of flow movement through the ditch in order to keep the velocity up around 1 foot per second. If we're required to achieve denitrification, we can do that quite readily in an oxidation ditch. One of the easiest ways, and I recommend this a lot to conventional oxidation ditches, if you want to nitrify, just turn your aerators off for about 4 to 6 hours per day. Let the basin go anoxic and we can denitrify. That saves energy because we're not running the aerators as much. We'll produce better effluent quality by reducing the nitrate concentration significantly. And we'll also generate alkalinity, which will help with the process as well. Now, typically, the capital cost of an oxidation ditch facility compared to conventional activated sludge, the cost will be about 20% higher. So ordinarily, we don't design an oxidation ditch or extended aeration activated sludge for design flow rates above 10 MGD. Occasionally it's done, but generally they're good for small and medium-sized facilities where the design flow rate is less than about 10 to 12 million gallons per day. Another version of the oxidation ditch is the Orbital process. And the Orbital process has typically 3 concentric rings. The outer ring, the raw wastewater and the return sludge come in first to the outer ring, then it goes into the middle ring and then into the inner ring. But we try to maintain a DO concentration of about 0.0 to 0.3 milligrams per liter dissolved oxygen in the outer ring. And the reason we keep it that low is because we want to simultaneously nitrify and denitrify. We know that the nitrifying bacteria are obligate aerobes, but even at 0.1 milligrams per liter, they can nitrify. The nitrification rate will be slower, but we've got a fairly long hydraulic detention time. And when the DO is less than 0.3 milligrams per liter, we can also denitrify. The heterotrophic bacteria can actually use nitrate as their electron acceptor and convert the nitrate to nitrogen gas. And so we're getting conversion of ammonia to nitrate by the nitrifying bacteria, and then our facultative heterotrophic bacteria will convert the nitrate to nitrogen gas. So both reactions can occur in that outer zone where we keep the DO fairly low. The middle ring will keep the DO about 0.5 to 1.5 milligrams per liter, and the inner ring somewhere in the 1.5 to 2.5, or maybe as high as 3 milligrams per liter, to make sure we have low ammonia in the final effluent. Here we have in the upper left-hand corner of this aerial photograph, you can see an actual Orbital process in the state of Tennessee. 3 rings, outer ring, middle ring, and inner ring. And you can see here's some of the horizontal disc aerators, and then there's a shaft with aerators here and here. So you have aerators located on 4 different shafts, and they supply oxygen and mixing to the reactor. This gives you an idea of what the horizontal discs look like. They're discs that have little notches on them, and the notches, as those discs rotate in the water, they provide oxygen transfer and also keep the biomass in suspension by helping maintain a horizontal velocity in the mixed liquor. So again, the Orbital process gives you the opportunity to, if you have fairly stringent limits on total nitrogen, if you have a total nitrogen limit of about 8 milligrams per liter, with an Orbital process, you should be able to meet that almost all of the time. Can it meet a total nitrogen limit of 5 milligrams per liter all the time? Maybe not, but it will meet it probably most of the time. So it does a good job, again, of nitrification and denitrification, and so produces a very high quality effluent. About 50% of the volume will be in the outer ring, about 1/3 of the volume will be in the middle ring, and about 17% of the volume will be in the innermost ring. Another extended aeration process is called countercurrent aeration. It's a circular reactor, and we have a rotating bridge that has typically a fine bubble diffused air system attached to it that'll be about 1 foot off the bottom. And that rotating arm actually moves around the ditch. And again, the diffused aeration system is attached to it. And as it moves around the ditch, then right behind where the aeration equipment is, we'll have fairly high dissolved oxygen, maybe 1 to 2 to 3 milligrams per liter. And as you get further and further behind the rotating arm, then the DO may actually go near zero, so that with this process, you may actually be able to also nitrify and denitrify within the biological reactor. The process is typically, the Scherer process is one of the more common designs or manufacturers that make this type of system. And you can see this is a system I'm familiar with in Alabama. You have 4 Scherer units in the upper right-hand corner. And this plant's designed for an average daily flow of 4.8 million gallons a day. Each Scherer reactor has its own dedicated secondary clarifier. The effluent from this facility has less than 5 milligrams per liter BOD, less than 5 milligrams per liter suspended solids. Ammonia is usually 0.1 or 0.2, and total nitrogen typically in the 10 to 15 milligram per liter range. And this particular plant has an ice cream plant that comes to it that provides a relatively high organic loading. And so, but the process works well. Fine bubble aeration again, the air helps provide mixing, but the moving arm itself, even if the air is turned off, the moving arm itself will provide some mixing of the biomass. We'll typically keep the DO around 1 milligram per liter. And again, that's low enough to still achieve nitrification, and then will allow lower DO to occur further back from the rotating arm that can promote some denitrification. Sequencing batch reactor. This is activated sludge in the batch mode. And this particular drawing, you see 4 biological reactors or 4 SBRs. So we have multiple units because we're operating in the batch mode. So while one unit may be in the react mode and another unit may be in the fill mode. And we have, if we're using conventional SBR units, we'll need more than one reactor because of the batch operating principle. So we go through several steps. First of all, we'll go through the fill mode where the incoming wastewater is brought into the reactor. Then after we fill the reactor, we'll have typically if it's a fully aerobic system, we'll turn on the aeration equipment and we'll aerobically react for a period of time to achieve biological metabolism. Then the third step will be the settle phase. We turn the air off and we allow the biomass to settle within the reactor itself. And that's one of the advantages of the SBR process. You don't have to have secondary clarifiers because you settle within the reactor itself. You don't have to have separate return sludge because there's no need to return sludge because it's all in the reactor. So there's about a 10 to 15% capital cost savings because of the lack of need for secondary clarifiers and the lack of need for return activated sludge. So after we go through the settle phase, then we go into the decant phase where we actually decant the clear liquid off the top. We may decant 3 or 4 or 5 feet of liquid volume off the top, and it'll be discharged to a post-equalization basin or to the receiving stream. And then to finish the cycle, we may have a short idle period before we begin the process again in the batch reactor. As I said previously, it operates in the extended aeration mode. We'll have detention time in the order of 24 to maybe even 48 hours. Most of the plants I'm familiar with are typically about 24-hour hydraulic detention time. Operate typically 3,000, 3,500 milligrams per liter mixed liquor solids. Again, a fairly low F/M ratio, long sludge age, and the organic loading tends to be low because it's, again, low rate activated sludge. So comments about the SBR process. Again, it's a fill and draw process. The reactor is basically completely mixed because when we turn on the air during the react period, There's good mixing in the reactor. Sometimes it's supplemented by mixers. Again, you have the savings because there's no cost savings because no secondary clarifiers we mentioned. And we have to have multiple reactors because of the batch process. We'll use automatic decanters that will decant during the decant cycle. And generally will produce excellent effluent quality. Normally BOD5 and suspended solids, most of the SBRs I visited will be less than 10 milligrams per liter and often less than 5 milligrams per liter each, low ammonia. And if we use anoxic cycles in the cycle, then we can also achieve denitrification as well in an SBR. Again, overall detention time about 24 hours. So again, it's low rate activated sludge. We use jet aeration or diffused aeration. The process is flexible. Again, we can incorporate anaerobic and anoxic zone or modes in the overall cycle, and we can produce outstanding effluent quality. And this biomass actually settles extremely well because it's not a continuous flow secondary clarifier. It's a batch settling tank. And when the influent is shut off, we get excellent settling during the quiescent period of the settle period. Now, we also have a process called the Ichthys process where the SBR is actually fed on a continuous basis. And for that system, we'll have a pre-reactor chamber that the raw wastewater is brought into and the return sludge, well, raw wastewater brought into the pre-react chamber, and we feed the wastewater into the SBR zone, and we actually achieve settling in the SBR zone, and even though it's operating in the continuous mode, and can produce excellent effluent quality operating again in a somewhat continuous mode. So as far as the cycles, again, fill, react, settle, draw, or decant, and then idle. The cycles can last, in this case, you get 3 hours of fill, 2 hours of react, half hour settling, and a half hour of decant. So a total cycle time of 6 hours. So there are 4 cycles per day. Some plants will have 6 cycles per day, and each cycle is 4 hours. Some plants will have 5 cycles a day, and each cycle will last 288 minutes. So it just depends on how the SBR is designed, but again, can produce outstanding effluent quality. Well, that wraps up our presentation today. Again, we have covered quite a few different types of activated sludge. Today, we looked at pure oxygen, a high rate process, expensive type of process, mainly used by large cities. And then we looked at low rate systems, several different types that produce excellent effluent quality. One thing I didn't mention is the low rate activated sludge process is basically the easiest type of activated sludge process to operate and maintain. So I always like to make the analogy in terms of activated sludge. It's like a 6-year-old playing t-ball. 6-year-old has trouble hitting a thrown pitch, but we set that ball up on a tee and he hits it quite easily. Well, I always call low rate activated sludge systems extended air, oxidation ditch, SBR, T-ball activated sludge processes because of the long detention time, low organic loading rate. They're very forgiving in their operation. They produce outstanding effluent quality, and they give us, again, some room to make some mistakes sometimes and still be able to overcome those mistakes. So again, thank you for listening today. Appreciate you being here. If you have questions or comments, you can contact me at the given email address, or if you have comments, you can contact Tom Winning at Oak Ridge National Lab. So thank you. Have a great day.